Okay, kids, welcome back to Mr. Murray's Mathland, and we are wrapping up our solids of revolution unit here with the last method you're going to learn, which is called the washer method, and we'll talk about why that is in a minute. But we're going to start right on the GeoGebra here, and here is the graph of 4 square root of x, that's f of x right there, and here is the graph of 4/27 x squared, so a portion of a parabola. They intersect at 9 comma 12. You can do the math on that if you don't believe me. But we're going to take this region and revolve it around the x-axis. So hopefully you can maybe visualize why the disk method we were working on wouldn't be good here. But take a look at this. So here's this. There's that region, and we're going to do the same thing we were doing before and revolve it around an axis. It could be a vertical axis, a horizontal axis. It doesn't have to be the x or y. But when you revolve that around the x-axis, notice how the region is not right up against the axis. See, there's some space right there between that region and the axis you're revolving around. There's space between there, and when you take a look at the solid that makes, you can see that it's going to leave like a hole in the middle. So we don't have a solid, bell-shaped object. It's got this kind of funnel that's like carved out of it. And here's why it's called the washer method, because if you take a cross-section at any of these spots, it's still going to be circular because you're revolving it, but it's going to have a hole in it. That hole being where that funnel, where that missing space there. And so all this really is just a variation on the disk method, that you're going to be finding the area of each cross section, and the area of each cross section is going to be that of a circle, but with a circle missing, a hole in the middle of it. So it's really a big circle minus the small circle. And so there's going to be 2 radii we're talking about. The radius of the big circle, and maybe here's a good angle to kind of see that the radius of the big circle would be from your axis all the way to the outer edge of your region. And your inner radius, the radius of the hole, the radius of the circle you'll have to subtract out, is that distance from the axis to the inner boundary of the region. So here, from the axis to the beginning of the region, and the axis to the outer edge of the region. But of course the distance is always to the center, which is that axis of revolution. That's an important thing to remember, because we're going to move that around. But so hopefully this helped you visualize, and now let's go do some algebra, right? But very cool, and that will lead us to the washer method. And Calc 2, maybe you'll learn the dryer method. Terrible. All right, let's go do some math. All right, let's grind this out here and put this washer method in action. So we're just going to compare it side by side with the disk method here, just so you understand the difference when you're presented with a problem. And the disk method, to recap, was when you take a region, and if the axis you're revolving it around, if there is no space between the region and the axis. So when you do that, it results in a solid block there, right? And meaning you only have one radius to worry about there. Any spot you take a cross section, you've got a radius, and that's it. There's no hole. So the disk method is pi r squared, dx or dy if you're going in that direction from whatever your boundaries are, a to b. But the just thing to remember, it's just a circle, so it's pi r squared. And the washer method is whenever you have a region and there's any space in between the region and the axis you're revolving around, that's going to leave a hole. And here is, by the way, if you don't know what a washer is, that's a washer, right? Those things that you get from IKEA to put in between the screws and all that. So I took this apart, and my bookshelf will probably fall apart now. But hey, it was worth it to show you guys a real live washer. So yeah, whenever there's not a banana republic, but if there's a gap between here and the axis, you get a hole. Oh God, enjoy these lame jokes, kids. You won't hear them much longer. So the idea here is it's just visualize a circle with a hole in the middle. And what's the area of a circle with a hole in the middle? It's, well, I guess we could draw it out here. It would be pi r squared, the big circle, minus pi r squared, the area of the little circle that's missing from the middle. So that's where I'm going to use big R and little r. It doesn't really matter what you want to call them, A, B, whatever, F, G. But pi r squared minus pi r squared, and since pi is the same, we could factor that out, and you're really dealing with pi times r squared minus r squared. So that is your washer formula, really. It's just pi times the integral of r squared minus little r squared. And again, dx or dr or whatever it may be from A to B. The big problem is always to be able to define what those radii are, and it does get a little more confusing because now there's two to worry about. So that is definitely where people can get a little mixed up. Hopefully you'll feel better about it after you see a couple of examples. And at any time, of course, if you want to just try it, hit pause on the video and see if you can do it, and then watch me play it out and see if you got it right. So here we go. Here's that problem that was animated there. 4 square root of x and 4/27 x squared. They intersect at 912. And we're going to revolve this around the x-axis. So if you remember, just this is what it looked like here. Kind of looked like this. You kind of got that shape and looked like that, right? And then you had this little hole in the middle. So the big thing, what's the big radius? Whenever there's space, we're dealing with a washer. That means 2 radii to define, a big radius and a small radius. The big radius is the distance from here to the outer edge of the region. So here all the way to the outer edge. And in that case, that distance would be top minus bottom, but it's going to be this 4 square root of x minus 0, or in other words, just 4 square root of x, because we're going to the x-axis. The inner radius, the radius of the hole, that would be this distance right here. There's the hole, or if you want to draw it more when it's out there, that radius is going to be the distance from here to the inner edge, and that's the parabola. So the inner radius is 4/27 x squared. So putting all that together, our volume is going to be pi times the integral from 0 to 9. We're doing this around the x-axis, so it's all about x values and keeping this in terms of x. So from 0 to 9 of big R squared, so 4 root x squared, and of course you could just call that 16x, minus little r squared, 4/27 x squared squared dx. And simplify as you see fit, and then go to the calculator. So let's see here. I actually had put them in here to look at the graphs earlier. So I've got that y1 is my 4 root x. So maybe a little shorthand here. So pi math 9 from 0 to 9 of basically y1, so alpha trace y1 squared minus y2 squared with respect to x. Boom, 1221.451. 1221.451. Okay. So a follow-up example is, well, what if it's the same region, same equations, same intersection point, of course, and yes, they intersect at 0, 0. Maybe that should be said. But what if we revolve it the other way, around the y-axis? So you'll be going in this direction, and there will be that was a pretty terrible washer, but the radius now, the big radius, will be from here all the way to the outer edge. So from there to the parabola, and the inner radius will be from that axis to the inside of the boundary. So you go from the axis, and then the first piece of the region you hit, that's your small radius. And you go past that all the way to the end of the region, that's your big radius. And if you're going horizontally, going around the y-axis or any other vertical axis, you got to put it in terms of y. So this shouldn't be too hard. We've got y equals 4 root x. So divide by 4, square both sides, and we'll have x equals y squared over 16, right? And this one is y equals 4/27 x squared. So we're going to multiply by 27/4 and take the square root of both sides. 27/4 y equals x squared. Take the square root. And you would use plus or minus algebraically, but this is just the positive side, so you can just use the positive square root. And so this is a dy washer. Your big radius is from there all the way out to that parabola, which is root 27/4 y. Your inner radius from the axis to the beginning of the region, the width of the hole, the width of the space, that is the y squared over 16. And so our volume is going to be pi times the definite integral. And now we're going in terms of y values. So on the y-axis, we're going from 0 to 12, right? Focusing on those y values. So sometimes an easy thing to overlook. And big R squared, root 20, well, actually that'll work out nicely when I square that. It'll just be 27/4 y minus this squared, and you can call it y to the 4th over 256 if you like, or just if you're feeling lazy. Got all that, dy, and let's see how that volume compares. Pi, math 9, from 0 to 12, and 27 over 4 times x minus, like I said, x to the 4th over 256. I just didn't feel like using all those extra parentheses, but whatever. And you get 916.088. I think we've seen this before in some of these when we've done it two different ways of the same region, and it was taller in this way. If you were to draw this out, going from 0 to 12, it's a taller thing, but not as wide, and so the wider one always gives you a greater volume, whereas this one, it was sure 9 units long, but like 12 units wide at its widest, so those circles were very big, giving you big volume. All right. So there's two examples. If you feel good, hey, you could be done right now. If you wanted to see a couple more just to solidify this and feel good, I'm going to take one region and I'm going to do 3 different problems with it. Or maybe you can come back to this, whatever, if you had some trouble on your homework. So we're going to find the volume of the solid obtained by revolving the region bound by the cube root of x, y equals 0, and x equals 1. And that is right here, of course. And I shouldn't really have to tell you that is at 1, 1 on the cube root function. So it's kind of a nice easy region to work with and to show a few different examples. So part A, if I revolve this region around the line y equals 2, line y equals 2 would be up here. And this region, there is space between this region and the axis of revolution. So if I revolve this in this direction, it would be up here. There's going to be a hole in the middle. There's going to be a space. So this is going to be a washer. And are we doing a dx or dy washer? If we're going around a horizontal line, which is really just like the x-axis just moved around, that's dx. So think any horizontal line is like the x-axis, which means dx. So now let's define those two different radii. What's the big radius? That's the distance from the axis of revolution to the outer edge of the region. So draw a line from here all the way, keep going. There we go to the edge of the region. And that is actually, top minus bottom. That's just 2 minus 0. That's 2. It never changes no matter where you draw it. So the big radius is 2. The inner radius is going to be a variable expression because that's the distance of the space, and that of course is changing as you go along here, but it's still going to be that distance from the axis to the inner edge of the region. So from here to when you first hit that curve. And what is that distance? The distance between 2 and the cube root of x. Top minus bottom, that could be called 2 minus the cube root of x, right? That's all you'd be doing is subtracting the y coordinate from 2 to get this distance. So 2 minus cube root of x. And once you've got that, this part is almost, it's almost a given. It's just a formality, hopefully. But still, even pressing the buttons, inputting it takes a little practice, right? So we're going pi times the definite integral from 0 to 1. Those are our boundaries. And big R squared, so 2 squared, or 4, minus little r squared. Now little r is 2 minus cube root of x, so you got to make sure to use parentheses around that and square that. And I don't think you want to FOIL that out, so we'll just leave it that way. And then we'll go to the calculator. Pi math 9, here we go, from 0 to 1. 2 squared is 4, I think I can manage that. 2 minus the cube root button, that's right in here in the math menu, cube root of x. Close that set of parentheses, square that small radius with respect to x, and here we go. 7.539, which then rounds up, so 7.540 or 7.539 if you want to truncate. And there you go. Okay, taking this same region and revolving it around the line x equals 1. The line x equals 1 is right here. You're revolving this around this axis. There is no space between the region and the axis. This is a disk method. There's no space in the middle. There's no hole. So it's a solid block. It's a disk. You're going around a vertical axis, which is just basically the y-axis, just moved around. So that is dy. Now, with disk, you only have one radius to define, and that is the distance from here, from the center to the edge of the region, right? Because it would be revolving in this direction, and there would be your circle, so your radius is right there. And the distance from here to there, well, you've got to change this since you're doing dy. You've got to take this y equals cube root of x and solve it for x. Well, that's easily done. X equals y cubed. So that is this function in terms of y. And right minus left, right? It will give you that distance no matter where you're at. It's the difference between 1 and whatever this x value is, which is y cubed. So 1 minus y cubed. And I guess you could treat every disk method as a washer if you liked. It's just the inner radius would be 0 because there's 0 hole. But pretty lame if you do that, right? So volume, pi 0 to 1. That's also the limits for the y values of the region from 0 to 1. Just that big R, 1 minus y cubed squared dy. Second pi, math 9, 0 to 1, parentheses, 1 minus x cubed, close that, oh, get out of that exponent, close that, square that, x. 2.0195, and again that rounds up 2.020 if you like, or 2.019 if you want to truncate. Very nice. And one more here. We're going to revolve this around the line x equals -1. X equals -1, another vertical axis. So we're sticking with it being in terms of y. So x equals y cubed. And we're going around the line x equals -1, which is over here. So I'm revolving this around this. And if there's any space, you've got a hole. So we got ourselves a washer. And so this is a dy washer. The washer, it's dy. What's my big radius? The big radius would be this distance from the center, which is the axis, right? If you want to draw that other side there, this would be all revolving around this. Here's the center. From here to the outer edge of your region. From there to there. And no matter where you draw that, that distance is not changing because this is a nice vertical line. So the big radius is going to be right minus left, 1 minus -1, which is, of course, just 2. It never changes. The small radius, the radius of the hole, that is changing because that's the distance from here to the curve. So at every given spot, that's going to be a different distance, and that is going to be right minus left, and the right boundary is the curve y cubed minus -1. So that will be +1, right? There's your small radius, there's your big radius, and here we go. Let's go. Last problem. Let's finish strong here. Volume pi from 0 to 1 on the y-axis of big R squared, so that's 2 squared or 4, minus little r squared, y cubed plus 1 squared dy. Okay. And here we go. Pi, math, 9, 0, 1, 2 squared, 4, minus, parentheses, x cubed plus 1, close it, square it, dx it. 7.405, very similar value to that first one, but not quite the same thing. So it's not quite the same shape. It's similar, it's got similar dimensions, and we revolved it around an axis that was about the same distance away, but not exactly the same. So 7.405, there we go, kids. That is the washer method, and that is a wrap on Chapter 6 and AB Calc in the year 2020. All right, so try the homework problems. Ask me if you got any questions. Come to a Zoom. Say hi. Whatever. Take it easy, kids.